Good morning, everyone. On behalf of Fundu Info and Shamant Shankar, this is Shiladitya Basu welcoming you to our webinar on architecting streaming analytics apps for rapid business value. Today, our speaker is Sid Chaudhary, VP of Product, YugaByte. Before we start, a little bit of housekeeping. Please use Ask a Question button at any time. However, we will take all your questions and answer them at the end of the webinar. And as you leave, please rate the webinar, leave us a feedback, and don't forget to share it with your team or network. Webinar would be recorded, and the recorded version would be available on demand after a couple of days. Without further ado, Sid Chaudhary.
Hello, everybody. Good morning. Great to be talking to you today. Here is a quick agenda that I have in mind. I want to just introduce myself a little bit more, then talk about why streaming analytics is all the rage today, some of the critical challenges in architecting streaming analytics applications, and thereafter I want to showcase YugaByte DB as to how we have architected it for those challenges. I have a real-world example with a live demo, and then we'll spend time in Q&A. Just a little bit about me. I started my career as a software engineer in Verizon doing telecom IT infrastructure. Thereafter, I spent about 5 years at Oracle and thereafter 2 years at Salesforce building identity and application platforms. Especially for real-time streaming analytics, my last two companies, AppDynamics and OpsClarity, were in application and infrastructure monitoring, which is essentially a good application of the real-time streaming analytics problem. I got to learn a lot at those places. Last but not the least, what I'm most excited about today is YugaByte, where we have built world's first transactional scale-out database with support for both non-relational and relational data models. We support key value, flexi schema, as well as distributed SQL as the three models or APIs to interact with the database. And I want to point out how the key value and flexi schema APIs are specially tailored towards the real-time streaming analytics problem. With that, let's dive right in. Why streaming analytics? I think it's good to take a few minutes to just understand why this is so important. So as in IT professionals, we are well aware of the systems of record that run our business, and the intelligence we derive out of them is essentially business intelligence. In this world, the time to insight from when your data landed into the operational systems, then went into your data warehouse, the data marts kicked in, the various tools and reports analyzed that data, did the joins across various other data sources, and finally the information was presented to the user. That time to insight was probably still today is in the order of weeks, months, quarters, and annual. This is because this is the system of record. It doesn't change that often that we need to keep on refreshing our orders page every now and then. However, when we go to the world of systems of engagement, and that's where streaming analytics kicks in, because the time to insight is much lower. It's in seconds, minutes, hours, and can be in days. So what are systems of engagement? Think of it that every consumer application that you interact through your mobile phone is a system of engagement, whether it be your Netflix, whether it be your Uber, whether it be your Airbnb, Amazon.com, they're all, in a way, they're our systems of engagement. Application developers are constantly trying to understand what we are doing in those systems, trying to improve our experience rapidly, not wait for days, months to come back with feedback, right? And that's the end applications is what we interact with on our mobile phones or on our web pages. But how does the data that one click that we do on the phone, and how does it manifest itself in the real-time application? That entire world is essentially broken up into three parts. First is the ability to ingest those clicks those streams. Thereafter comes the ability to process those streams into something meaningful that can be then presented back to the users. And last but not the least, we need a database to store that both the raw data as well as the processed insight. And if you see, this world is slightly different than the business intelligence world, because the volume of data is extremely high compared to the system of records world. Now, how do we create value? As architects, our goal should be to create value for business. And that's what we are paid to do. So at the end of the day, it's about two things. First, we have to increase the return on investment on our current application, current infrastructure with amazingly happy customers. And that happens by having timely and actionable insights that we show to them. Netflix personalization is a great example of that. If it starts showing us movies that we don't like, then we are not going to come back to Netflix, right? So timely and actionable insights. Low latency page loads. It's extremely important. As users, our perception is very strong. If something is loading slow, we know it immediately, and we're not going to come back. However, if something is amazingly fast, we love that experience. We want to come back to it again and again. Additionally, there should be no data loss. I do not want you to tell me that you lost one of my, Uber, let's say, taxi requests. And I do not want you to tell me that, well, you're having an outage because that is exactly the time when I need my Uber to come by. So this is how we create happy and loyal customers for our business. Secondly, if we take an inward view of the world, it is about decreasing total cost of ownership by changing the happiness from customers now to happy developers, happy operations engineers, as well as happy business teams, the teams that actually fund our development operations. Usually what happens is if you build something successful, then your data stream that you have to ingest and analyze becomes unpredictable. Imagine the challenge that Uber has. They really, for normal days they may have figured out how much cab rides they will have to issue across the globe. But when there is a big event, let's say New Year's Eve, it's sort of hard to predict how much actually will be used and how much it will go to, say, your competition. So as IT teams, our goal is to ensure that that unpredictability in the business and unpredictability in the data stream can be handled by the systems we design without increasing labor cost. The systems that we put in should be able to handle that without adding more manpower to the problem. Secondly, again, as business, we all have experienced this. Once we do something successful, business would like to add more features, more applications to the same infrastructure that we have added. If we tell them, no, we have architected it very rigidly and you cannot change it, and changing it will take 6 months, then that's not a happy business team, and ultimately that unhappiness will carry forward to the dev and operations team. So what I would like to walk you through is in terms of the streaming analytics infrastructure, how do we create business value around increasing ROI and decreasing TCO? So let's go into architecting. So what are the sort of the top 3 challenges or architectural challenges in building such streaming applications? So first and foremost is that ingestion of that data firehose fast and without loss. And that usually requires a reliable, high-performance streaming platform, which can take the events in, can quickly store it into some temporary store, and it's usually a store and forward mechanism, and then make it available really fast to the processing engine or to the database. Raw events on their own are not very useful. We derive intelligence by by aggregating that information and seeing trends on them. And also aggregating this information on the basis of a single user helps us to guide the user saying, hey, you have been doing this kind of actions over the last last week or so. Would you like to, you haven't done that today, would you like to do it? I mean, we are starting to see these kinds of experiences starting up in our mobile applications. So what infrastructure is needed for that? And at the core of it, you need an ad hoc real-time analytics framework that can analyze data over a moving time window. You see, this is very different than BI. BI requires us to look at a very vast amount of data that goes for like 3 months. Whereas here we have to look at since the data volume is higher, the vast amount of data is probably still true, but here we have to analyze in smaller chunks. We have to analyze in seconds, minutes, hours, and days. Last but not the least is the database for streaming apps I talked about. You need a reliable storage, management, and serving for this ever-growing data streams and ever-growing insights that we're generating. So the world has sort of started standardizing some of these standardizing some of these infrastructure elements. Kafka has risen above the crowd and has become the de facto high-performance streaming platform. We'll see why that is the case. When it comes to this ad hoc analytics aspect, there are two emerging technologies. One is Spark streaming, and the other is Kafka's own Kafka SQL. And each has its pros and cons. We'll talk about it, how to go about doing it. There are many more actually. Apache Flink is there. Then there is the new version of Apache Storm, which is called Heron. So there are multiple ways of doing stream processing, but we'll touch on these two for the purpose of this talk. And when it comes to database, we have YugaByte DB, which we have purposely architected for solving this ever-growing data management problem. So why Kafka and KSQL for stream ingestion and processing? Let's start with Kafka. So there are 4 aspects that make Kafka so amazing. First, it is highly scalable. You can start very small. You can have a 3-node Kafka clusters with a few partitions and a few brokers, a few consumers and a few producers. Everything can be small. You can build your application. And then if your application becomes successful, volume needs to be increased. You just keep on adding nodes and Kafka will manage the scalability problem for you. And that is something that we didn't have before Kafka's advent in LinkedIn. Fault tolerance. Any reliable distributed system requires strong fault tolerance characteristics because especially when you are running on public cloud infrastructure, anything that can fail will absolutely fail. So failures mean unavailability, failures mean data loss. We have to avoid that. And Kafka is architected specifically to not go with not have those kinds of challenges. Integration breadth. Almost any technology that you can think of which can emit data or it can store data, which is emit data is the layer at the top and store data or consume data is the layer at the bottom. Today there are pre-built integrations or connectors to Kafka, and that provides an amazing I would say developer agility when it comes to building these streaming analytics applications. The sum total of all of this has led to Kafka's wide adoption. Almost any use case you can think of, it will probably somebody or other would have implemented it in Kafka, would have blogged about it, would have shared their experiences at Kafka Summit and so on. So if you want to become part of a good ecosystem, this is it. Now let's move to KSQL. KSQL stands for Kafka's SQL processing layer. It's a very interesting built-in stream processor on top of Kafka, and it is excellent for some simple aggregations as you're starting to build out your application and do not want to pay the infrastructure penalty of a separate stream processor altogether, right? And that's when you can just click on a button and your KSQL is turned on. You can start analyzing the information or the events that are passing through Kafka, and start validating whether your application is directionally correct or not. And the demo that I have today is actually using KSQL because it's so simple and easy to use. Now coming to the big boy, which is Spark streaming. Spark has been around for quite some time, but Spark streaming is sort of a is a newer, I would say, newer kid on the block in terms of an application on top of the Spark engine. Now, what it does is it actually takes the data stream and makes it into very small batches of input data, and then uses the same Spark engine that you use for regular offline big data analytics. It just uses the same engine and then emits the process data out to whichever place it needs to be stored in. So clearly, Spark streaming, by virtue of it being there for a longer period of time, it is more general purpose than KSQL. You can run a lot more variety of aggregations on top of Spark streaming than KSQL. Spark engine, once you install, deploy this infrastructure, then you have the ability to augment this with machine learning, do interactive analytics with Spark SQL. So there are additional libraries that help you, exploit this infrastructure for higher value. But the cost is that, when you're starting out, if you go with this, you have introduced complexity and additional infrastructure, one more distributed system into the problem, and that can have, that will lead to increase in cost. Coming to why YugaByte DB as the stream database, there are a few things that I want to point out. First is about strong consistency and ACID transactions. At the heart of it, these things mean that when you store something in this distributed database, you can immediately get the same data back. Usually distributed databases do not have those guarantees. Essentially all first generation NoSQL databases did not have these guarantees because they used something called as eventual consistency. So if you write something to it, you cannot immediately read it. And that is the ability to read what you just wrote is very important in streaming analytics if you are trying to get an accurate picture or accurate aggregation of the streams that are coming in. Secondly is elastic scaling, same as Kafka. If you increase the size of your Kafka cluster, because more data is coming in, you can similarly very elastically scale the database to add more nodes, get more write throughput and read throughput, and sort of remain balanced with your Kafka side of the house. High fault tolerance, again, very similar characteristics as Kafka. Data never gets lost. And if there is an outage, then there is an auto failover built into the system, and the system self-heals with that auto failover, and things proceed as if nothing has happened. So failures are transparent to the application clients. Low read latency. This is a very important aspect, especially when you're building user-facing real-time applications. As I pointed out, users are susceptible to increase in latency. So when you want to read the data, you want to serve correct data and at the fastest rate possible. And YugaByte DB does that. I actually have ways, the details of how we do that. High data density is an important aspect because we're talking about ever-growing data streams where maybe terabytes of data are being ingested on a daily basis, and overall you have to manage at a petabyte scale. And that's when you want to have each node having tens of terabytes of data, so that you are, in order to sort of run a streaming analytics infrastructure, you are not running 100 node systems, but you are actually doing it a fraction of that those sizes. It makes it easier for your dev and operations team to sort of manage and build on top of them. And finally, this is true with most NoSQL systems, the ability to automatically expire older data for whom we have already generated the insights, and we actually don't need to continue to keep them around. And because keeping them around means we're paying storage costs, and sometimes those data are involved in queries, which means they may have the impact to potential impact to slow down our queries and so on. So with that in mind, here is the architecture that sort of is coming out to be a good business-centric architecture for streaming analytics application. You take the streaming data from devices, sensors, and applications, stream them into the Kafka streaming platform. Kafka has some temporary basic storage, but if you want absolute lossless infrastructure, you have to store it in YugaByte DB, where each and every record is guaranteed to be never lost. And then you run your real-time analytics on top of it by reading either the stream, or you can even read off of YugaByte DB. You model your queries, and whatever be the derived insight, you write it back to YugaByte DB so that you can power the user-facing application off of YugaByte DB. Additionally, you can actually read the derived tables and start generating alerts and push notifications back to the user. One can be if this is your mobile application, then this is your mobile notification, push notification. So that's how the architecture looks like. With that, let me dive a little bit deeper into why we believe that the business value I talked about is served by YugaByte DB the best. So I've talked about YugaByte DB, but I haven't introduced it. So we're a transactional Planetscale database for building high-performance cloud services, especially that run in public cloud infrastructure, where infrastructure is unreliable, but you need high performance and zero data loss. There are two key things that we add to the world of databases. We give application developers and sort of an unparalleled data modeling freedom, because on top of a common database engine, we have three models to interact with the data: key value, flexi schema, which is sort of document data types, and finally the most complex one is relational, where keys are dependent on each other. Second aspect is the ability to run in a cloud native world. Cloud native essentially means that you are cloud agnostic. You can be multi-cloud. You can run on Amazon, Google, Azure, all at the same time with similar performance semantics, or you can run on a infrastructure abstraction such as Kubernetes, which hides away your underlying infrastructure altogether. So with these sort of guarantees, the way we achieve these guarantees are through these design principles, where we have ensured that in terms of transactional, it's not just about our classic multi-shard, multi-key transactions, but also the very simple single key should be transactional, single key access. That means if I write one event into the database, it should not get lost. Right? That's a very important guarantee from a database. And I talked about how all of this is built on a common single storage engine, which is actually document-based and strongly consistent. Low latency and high throughput are sort of core to the database, because especially if you're building streaming analytics applications, you have to ingest at a very fast rate and you have to serve at a very fast rate. Slow kills, especially things in systems of engagement. Planetscale now, when our streaming app becomes very successful, we would like to spread it out to a multi-region deployment, so that users who are interacting with that system are seeing even less latency than they used to do before in a single region infrastructure. And that expansion from a single region to a globally distributed deployment is something that we have made extremely simple, so that as you succeed, you don't have to worry about how do I scale to scale globally across multiple data centers. Cloud native, touched on it, built for the container era, runs inside Kubernetes, self-healing. Last but not the least, the entire project is actually completely open source. It's Apache 2.0 open source, and the APIs that you interact with it, the key value is compatible with the Redis command library. The Flexi schema is actually compatible with the Apache Cassandra query language, and the relational API is actually compatible with PostgreSQL. So not only we're open at the core, we're open at the API layer as well, because we essentially want our users to feel that they actually are not getting locked into a new database, but they have the flexibility to come in and come out as often they wish. So a little bit of technology now. What does it look like underneath a distributed database? So we have a 3-node cluster here. On top of the 3-node, first there is something called as a master, which its only job is to manage how various shards are located on various nodes, as well as do cluster-wide system operations. It is not part of our regular database application client to the database interaction, because those are handled by the IO nodes, and that's called the T server, or it stands for tablet server. Now each tablet is a shard of a table, and you create tables inside YugaByte DB, whether it be of any of the 3 APIs, and that immediately the moment you create a table, this kind of a sharding system is built underneath for you, so that as data comes in, it automatically starts going into different nodes, and never you get into a situation where a single node becomes or the system overly becomes reliant on a single node, because if that is the case, then when that node dies, then the system is under tremendous pressure. In distributed systems, whenever we want to create multiple nodes, we want them to be evenly balanced with our data. And these are some of the underlying technology innovations that we have brought forth in terms of what we know as a DocDB storage engine, which is a document-based storage engine, Raft as the consensus replication layer between the various nodes, as well as during failures, how do we elect new leaders for the tablets. And finally, there is overall there is a distributed transaction manager which ensures that our asset transactions, even across multiple rows, across multiple shards, is correctly tracked and correctly committed. With that architecture, what I want to show is how we create business value. So first business value is that of zero data loss. And the way we do that is when a client connects to any node in the system, and in this case, the client is saying, I want to update a record in tablet 3, but it connected to this T server 2, and it does not have the tablet 3 leader. Only the leaders can do the writes and take the updates. Then the system automatically redirects completely transparently to the client to the node that has the leader. And now the leader's job is to ensure that not only it updates itself, but it also updates the 2 replicas that are present, but wait for only one of them to acknowledge, so that the right quorum is established, which is 1 me and 1 of the remaining 2. So 1 plus 1 is 2. And in a 3-node system, 2 is quorum. And then once that 2 quorum is established, you acknowledge back to the client that, hey, quorum has been established. Now your data is safe. Why do I say data is safe? Because at this point of time, I'll show you if there is a failure, you're absolutely guaranteed that the same data that you wrote in the previous example will be available to you. Let's take the example of now assume that we had a loss of this node altogether, and those the T server 2 and the master 2 are no longer available. Now, immediately the remaining 2 followers will realize that they have lost their leader, and that's when new leader election happens automatically. And the tablet 2 leader, which we lost from this side, is now created here, so that tablet 2 can continue to be updated. Now, if this client is trying to update tablet 2 and he sees that this node is down because it's no longer reachable, then system automatically again will redirect it to the place where the tablet 2 leader is there. And now it can ensure that the same write path that we talked about, and ensure that a majority commit is made, and then finally the client's request is acknowledged back. This kind of a system and the zero data loss and zero downtime sort of go hand in hand together. When we do the hard work on the right path to ensure that enough copies are updated, we can absolutely ensure that your system functions with zero downtime, because losses are expected and the system will self-heal. Low latency. Now that we have taken care of the zero data loss and zero downtime business goals, one of the business goals we established was low latency. Don't take time responding to my queries. Almost every user is implicitly telling us that. So in this case, and give me the correct data, by the way. It's easy to give incorrect data very fast, naturally. So here, in case the client, if I'm reading something from tablet 3, then immediately all I have to do is go to the tablet 3 leader and serve the data from there. And I'm absolutely guaranteed, since tablet 3 is the only way new data can enter every record inside the tablet, the data that is being served is the data that I had previously written to it. Very important in a streaming system. Or if I'm okay with increasing throughput slightly, but decreasing what we known as the consistency level of the system, it's still timeline consistent. You'll never see out of order data elements in there, but we can increase the throughput by simply reading off of the followers, which will have a slightly older copy of the data, and we can put guarantees saying that do not serve data from the followers if it is more than 5 minutes old, and that means that the system will automatically redirect such a request to the leader to start serving that information. Now coming to the cost side of the house, here the big thing, and this I have observed this in streaming infrastructure especially, most teams, engineering teams or operations teams actually over provision their infrastructure. They create bigger nodes with higher compute and higher disk, or they create more nodes altogether. Now that is not good, because at the end of the day you're drawing precious money away from the budget that was allocated to you. So as a system designer, our goal should be to how do we scale on demand and avoid over provisioning, and that's something we put a lot of thought into. So if you see that your throughput is no longer increasing, but your compute resources are already getting maxed out, let's say 60, 70, 80% compute is getting maxed out, then you know that this system can be served better if you add a new node into the system, because you'll release the pressure on the compute capacity that is present in the existing cluster by bringing in some new resources. Now, the moment a new node gets added, in case of YugaByte, it actually does a lot of smart things into play. It knows that it has to rebalance its leaders and rebalance its followers out of what's there today in the cluster. So in this case, the T server 1 was previously having one more leader compared to the T server 2 and 3. So the YugaByte DB will automatically move this tablet 4 leader to the T server 4. Thereafter, also has to balance the followers, and it knows that it can take one follower out from each of the remaining nodes, so that the net result will be that each of the nodes will now have one leader and two followers. Again, a fully balanced system has been created through automatic rebalancing as new nodes were added. Now, this system can handle more throughput than the system that was there before, because we have added the compute capacity of the T server 4. Very important as we go about thinking about how much infrastructure to provision. And if we can also decrease that, you can remove the node 4 anytime we feel like we don't need that additional capacity, and the system will do exactly the reverse of what it did, and it will go back to a balanced state again. Benchmarks. We all love benchmarks. How do we compare against the best of the best? YugaByte DB is 3x faster than the best NoSQL out there, which is Apache Cassandra. And especially in case of reads, the performance is tremendous, because on the read path, YugaByte DB does almost no work compared to a Cassandra. YugaByte DB can store a lot more data than Apache Cassandra, because of the core architectural underpinning that I talked about, as to how at any point of time, we're not talking about the full database. We're talking about leader shards and follower shards. And as a result, you can pack a lot more of those shards into a single system. And if you add new nodes, then some of those shards will move to those new nodes. A real world example. Let's look at what a real world example can look like. So what I have here is an IoT Fleet Management application, where trucks have sensors, and those trucks are going on various routes in let's say in our country, and those sensors are constantly emitting the location of those trucks back to us, and we as the as the sort of the fleet provider have to showcase back to our B2B customers as to the trucks that they have taken from us, how exactly they are running through the various routes, what truck is stuck at what point because of road closures. That's how we win the trust of our customers, who are paying us lots of money to rent these trucks, let's say, right? So it's a B2B fleet management application. And what we have done is we have built it on top of Kafka, KSQL, and YugaByte DB, which is we're calling as the Sky Stack. And it's fully open source. You can try it out on your own. Here is the link. Architecturally, this is what it looks like. The fleet is just moving around the globe. The location tracking enabled and IoT sensors emitting those streams of events into a Kafka cluster. We're constantly analyzing that information using Kafka SQL. This analyzed information, as well as the raw information, is stored inside YugaByte DB. And we have a Spring Boot application, which is the UI, to serve all this this data back to our B2B customers. Previously I had shown you a sort of an architectural blueprint. This is a concrete architecture with some concrete technologies baked in. We have full instructions on how you can run it. Install the Confluent version of Kafka cluster, install YugaByte DB, connect the Kafka Connect sync, and then just set up the various tables and streams. And all you have to do thereafter is just start the load. So let me go ahead and start showing you that. So right now, if I load this, nothing much is happening. Well, this is from the last hour. So what I'm going to do is I'm going to start additional load into this system, and you can see all this is doing is pumping in more data in terms of a event. with a vehicle ID, with a vehicle type, with a route ID, with latitude, longitude, as well as things like timestamp, speed, fuel level, all the things that you would expect an a IoT or sensor-enabled truck or vehicle to actually emit. And once you have that, you can see how we are, that same information is now getting persisted, raw data is getting persisted into the database, and then see, these two are both raw data elements because it's talking about the total traffic and the last 30 seconds window, and whereas this one is based on pure analysis of where the vehicles are stuck at because of road closures. Now, we just picked three different kinds of insights to show to our B2B.
Sid, one thing,
yeah.
Your screen is not visible. I'm not sure if you're sharing the screen at this point. You are planning to do that.
Oh, okay. I am.
Yes, now it shows up. Thanks.
Okay. Can you see it now?
Yes.
Okay. So maybe I missed. I'll go through this again. This is the IoT Fleet Management dashboard. All I did is pump in a new set of events into the system where all that the events are doing is sending me a vehicle ID, vehicle type, route ID, as you can see, latitude, longitude, and a timestamp, speed, fuel level, all the things that you would expect a IoT-enabled fleet to send us. And then on top of that, we have built these insights for our business customers, where we're telling them as to, what is the distribution of the various types across various routes. How is the traffic actually, going through a particular route, and which vehicle is stuck at what road closure, right? Again, the possibilities are endless around what exactly you would like to build on top of this data. But at the core of it, when you have a flexible infrastructure that I walked you through, using the combination of Kafka, KSQL or Apache Spark streaming, and YugaByte DB, you can build these applications lightning fast. You can test them out, you can deploy them at a smaller scale, and as you see the interest of the customers and the business grow, all you have to do is just scale without thinking again, because you chose the right architectural elements on day one. Hope that makes sense. With that, I would like to just note that you can try all the things that I talked about. Either just try YugaByte DB on its own right using our quick start, or this full IoT application that I walked through is available at your fingertips. You can even, if I click on this and go here, yeah, okay. You can see that even though I went through the KSQL side of the house, you can easily do the same with Spark streaming. It's slightly more complicated infrastructure because you have to run Spark streaming as well alongside the Kafka and YugaByte DB. But the steps are very much the same, irrespective of what exactly is the streaming application you use, because at the end of the day, the application is powered by directly off of YugaByte DB. Okay. With that, I've reached the end of my presentation. Thank you for the time. Would love to take any questions that may have come up since then.
Thank you, Sid, for a wonderful presentation. We definitely learned a lot about YugaByte DB itself and how Netflix does its suggestions. I have always wondered what type of movies it's going to throw me up next time. Anyways, we open the session for questions.
Looks like we're all good.
All right. This presentation will be available as an on-demand package a couple of days after this webinar. We hope you share it with the rest of your team, and you have the contact information of Sid so that you can reach out to him for any questions or concerns you may have. Thank you very much, everyone. And that brings us to the end of this webinar. Thank you.
Thank you, everybody. Have a good day.
You too. We do have a question, actually. How do transactional guarantees work in geo-distributed setups?
Excellent question. When it is geo-distributed, the thing that kicks in is essentially the difference in clock skew between the two regions or multiple regions that are present in the system. And thereafter, so each region that is participating in the transaction has a slightly different view of what they believe is the wall clock time. And that makes it harder for a transactional system to coordinate that commit across multiple places. And I'm assuming the question is sort of pointing towards that challenge. The way we at YugaByte DB handle that is through two things. First of all, we attach to a more reliable time tracking protocol than NTP when we are running on systems like Amazon and Google, because each one of them provides for their customers for free a better atomic clock than what you would typically get by a traditional NTP clock, which has absolutely no guarantees, so that the clock skew between the multiple regions that are participating in the transaction is lower. Secondly, we allow the user to configure what is the max clock skew that it is willing to tolerate in order to commit the transaction. And let's say that number is 100 milliseconds. And if the nodes are underneath that max, then we'll wait maximum of that 100 milliseconds before we fail the transaction. Or, if everything goes well, then it actually passes much below that. But let's say some of the nodes start going beyond that max configured clock skew, then YugaByte DB is sort of designed to ensure that that node is essentially not gonna be considered for the purposes of this transaction. It will actually be kicked out of the cluster altogether because it has deviated so far. The net goal is that if we commit a transaction, however higher latency it may be, it is absolutely guaranteed to be present in the system. If we don't commit a transaction, then that problem is essentially made clear to the application client so that they have to retry. These are sort of the best possible architectural guidelines you can come up with if you absolutely have to commit transaction in a geo-distributed manner. I hope that answers the question.
Yep. Anyone else? Any other questions? All right. I think we'll thank our audience again for taking the time this morning, and thank you to our presenter, Sid Chaudhary. From the West Coast, it's really early in the morning, and hopefully he won't get caught in traffic going to his office.
Yeah.
All right. Take care, everybody.
Thank you.
Have a wonderful day.
Bye.